Good day, everyone. Thank you for attending today's webinar on the revolutionizing cartilage repair. Combine the VitroGel system with a Bendable-Tip Arthroscopic device for controlled hydrogel extrusion, a part of our webinar series on VitroGel hydrogel for in vivo tissue engineering models. I am Christopher O from the Well Bioscience, and I will be your moderator alongside our speakers for today, Dr. Melissa Fergamino from the Well Bioscience, Dr. Danielle Guarnera from Regenerative Technologies Lab at Biorobotics Institute of Escuela Superior de Santa Ana. A few housekeeping. During this webinar, you can utilize the Q&A tab on your left side for any questions you have. We will collect and present them during the Q&A session. And along the webinar, we will have some quick polls. Feel free to participate as we go along. Also, the webinar will be recorded, which can be accessed later for your convenience. Let's begin. Dr. Melissa Fergamino from the Well Bioscience will start with a short introduction on VitroGel and the application uses. Afterward, we will turn it over to Dr. Danielle Guarnera to present his research on cartilage repair. Dr. Fergamino, I will turn it over to you.
Okay, thank you, Chris. Good morning, everyone. Thank you for joining us today in this webinar. So I will be taking the first few minutes to talk about VitroGel and why it is an excellent choice for in vivo and tissue engineering applications. So VitroGel is a completely xeno-free system, a completely xeno-free matrix that provides an easy-to-handle environment for injectable applications. It has unique injectable properties, which I will be explaining in a few minutes, and it also has tunable mechanical properties for different tissue and cell types. It's easy to handle and adaptable for minimal invasion applications. It maintains the structural integrity for extended period of times, and it supports cell viability, proliferation, and differentiation. To highlight some of the key features of our system, it's stable at room temperature. It's completely xeno-free. All our hydrogels are injectable. The experimental setup is really easy and simple, and it's also really simple to harvest the cells out of the matrix using our enzyme-free recovery solution. To compare VitroGel with animal-based ECMs, again, regarding the composition, our system is pure, completely synthetic, while animal-based ECMs have a lot of undefined compounds because they derive from mouse tumors. Regarding the preparation time with VitroGel, the setup, it takes up to 20 minutes, while with animal-based ECMs, it can take up to 2 hours. Also, our VitroGel is room temperature stable with a room temperature protocol. This allows researchers to not work with an ice bucket, and also it doesn't require dry ice shipping. This is not only cheaper, but also environmental friendly. Regarding the gel strength, we have our high concentration line of VitroGels that can adapt the mechanical strength of the matrix within a range to support different cell types and tissue environments. This is not doable with animal-based ECMs. So all in all, with our system, you save up to 80% of operation time and 40% of cost per test. These are only some of the advantages of our system compared to animal-based ECMs, but please feel free to scan the QR code to access our webpage and learn more. So to dig deeper into the unique rheological properties of our VitroGel system, all our VitroGels, as I already mentioned, are injectable. And they have these unique injectable properties that once you mix your cell suspension with your VitroGel, it creates a stable, soft hydrogel that can maintain its injectable properties up to hours at room temperature. But then, when you press a force, let's say with a syringe, it transitions to a free-flowing state. When this force ceases, there is a rapid recovery to the hydrogel form. So this is very important because researchers don't have to worry about needle clogging or needle breaking, and it also ensures that the cells will stay in place after the injection. All these properties are really important and makes VitroGel an excellent candidate for animal injection, droplet formation, bioprinting application, and lab automation processes. I want to show you this video that explains better the protocol that I just mentioned. You will see first our VitroGel being mixed with our cell suspension. Then this mixture will be transferred to a syringe. You will let it sit for 5 to 10 minutes. And then you will see that when you turn the tube upside down, the hydrogel is already formed. But when you apply the force, it becomes free-flowing again. Now we will see that when the force ceases and the tube is turned upside down again, the hydrogel is already recovered. Another feature that I want to highlight that is really interesting and important is that our VitroGel has a sure biocompatibility. So we have seen that after 8 weeks of in vivo incubation, there was no inflammatory response. We have some great references from big laboratories using our system successfully for this kind of applications. So to mention some of examples of our system being used for this kind of applications, in these top panels, we can see the protocol that I already mentioned. And in the bottom panel, we can see our system being used for a adipocyte-derived stem cell culture for scar repair. Please feel free to scan the QR code to access the publication for more details. Another examples of our model being used for this type of applications, today Dr. Garnera will be telling us about his cartilage model. We also have the ototoxicity model. This is a drug release experiment. Also the tooth root injury model and the invertebral disc model. Again, please feel free to scan the QR codes to access the publications. So we like to provide the end-to-end solutions for 3D cell culture. We do not only provide the VitroGel or the bioinks and the plasticware for the 3D cell culture, but also if you want to perform functional assays, such as invasion assays or angiogenesis assays, we do provide the kits for that. As I mentioned, if you want to recover the cells out of the matrix, you can easily do it with our enzyme-free recovery solution. And at last, if you want to perform downstream analysis, such as viability testing, you can do it with our Cyto3D Live Dead assay kit. So you can see here that we provide the complete workflow for 3D cell model establishment. So all in all, we like to build the future of 3D cell culture by starting with the end in mind with this xeno-free system, opening the door to clinical and lab automation processes with consistent results. Thank you very much for this time. I will hand it over to Chris again so Dr. Garnera can start his presentation.
Thank you, Melissa, for the great overview of VitroGel and how it can apply for in vivo tissue engineering models. Okay, our next speaker is Dr. Daniel Guarnera. Dr. Guarnera earned his master's degrees in 2015 from the Politecnico di Torino, focusing on pantograph and rigid catenary interaction, and completed his PhD in 2019 with a thesis on advanced numerical models for biomechanics. During his PhD, he collaborated with the University of Massachusetts on 3D printing human artery phantoms. In 2020, he joined the Regenerative Technologies Lab at Scuola Superiore Sant'Anna for postdoctoral research working on materials science, biomechanics, and computational fluid dynamics. He has contributed to various Italian and European projects, including at Memoria, Reborn, and BioMeld. Currently, Dr. Guarnera is a project manager for the Forget Diabetes EU project, developing an artificial pancreas, and is involved in designing bioactuators and biomedical devices such as orthotopic tool, bridging innovation and application in biomedical engineering. Dr. Guarnera, we will turn it over to you.
Thank you, Chris. Thank you, Melissa, for the introduction. I will share the screen. And okay, good morning to everyone. Thanks for attending. I'm Daniele Guarnera, and I will tell you about a novel arthroscopic device for the release and controlling hydrogel extrusion for the cartilage treatment. It is a device that I developed inside of my regenerative technologies lab within the Scuola Superiore Sant'Anna in Pisa. I'm a postdoc researcher of the Robotics Institute that is in Pisa, so I came from Italy. And my research focuses on computational models for tissue engineering, design of medical device, advanced techniques for tissue generation. And through these research fields, I joined different European projects like MyPro, Reborn, Biomed, and Admaiora, that is the father of this arthroscopic tool. So today, let's talk about osteoarthritis. Osteoarthritis is a joint condition that causes pain, stiffness, and mobility problems. 43% of people in Europe are with osteoarthritis and are in the working age, so it's not an only older people problem. You know that no treatments can stop or reverse these pathologies, and up to 54% have pain despite taking prescription for pain relief. Additionally, you can wait in a good healthcare system up to 6 months to have a joint replacement. And then, however, not everyone with osteoarthritis may be suitable for surgeries. So the Admaiora project tried to revolutionize this framework, exploring the potential of smart nanocomposite materials and stem cells interact with external physical stimuli, right? And Admaiora tried to do this revolution through 3 different lines with 3 different ingredients. So the development of biosynthetic hydrogel, the development of minimally invasive tools for surgical delivery, and a custom brace equipped with US probes to monitor and stimulate the implanted nanocomposite hydrogel. Today, I put my attention on the design and development of the arthroscopic tools with bendable tip to release and deliver biomaterials in cell right in situ. So, which is the state of the art? What is the situation currently? Normally, for the mild osteoarthritis, the most widely used treatment is the intra-articular injection. That for sure is really easy and quick. There are no side effects, and it's very cost-effective. But in the same time, there are very short-term effects. There is no steady and choose no accuracy. For the most ever case, the most innovative kind of treatments that you can receive from the healthcare system and from research also is the in vitro bioprinting, that for sure you can build a very accurate morphology of the construct to put inside the cartilage, the cartilage of the knee. And there is a good assessment of the cell growth, but you require an open surgery and the possible structural mismatch. At the same time, also the in-situ bioprinting, that is a very novel technique. But also in this case, you can have a very high resolution and a Hydrogel extrusion. But also in this case, you don't have a dexterity because also the tool is quite big, let's say, and you require for sure an open surgery with a long restoration time. What is our approach? Our approach is exactly in the middle of these 2 kind of techniques. So between the intra-articular injection and the open surgery approach. So because of this, we try to design this kind of tool that is the arthroscopic extruder that is a handheld and in-situ device, can be used for sure in arthroscopy. So the times of surgeries and the restoration times are very, very small. And that bendable tip is disposable, is compatible with a large range of cell-laden hydrogels, and is compatible with the volumetric or pneumatic system for the extrusion. So I will describe the design and characterization phase, the testing phase, the biological assessment, and at the end I will show you the results of the usability test that we had with some clinicians that validated the device. So inside Admaiora, we have several partners. The most important ones was the Istituto Ortopedico Rizzoli from Bologna. This is one of the most known orthopedic centers in Europe. And the design of the tip was set in collaboration with them. We chose the nitinol for the material because of its biocompatibility and superelasticity. And we designed 3 different modules, of 30 degrees each one, for a total bending of 90 degrees. We investigated 4 possible designs, and we tried to assess for stress concentration, bending force required, it can resist bending in undecided direction, and also fatigue resistance. So the first phase was the computer models, so the computational models in which we assessed that there are no localized peak of stress, and then we moved to the lab at the instrument machine, in which we had several different tests. The first one was to assess the force required by the tip to be bent, and all the configurations, all the designs were exactly the same, around 4 or 5 newtons, allowing manual bending of the tip with the extrusive extruder, let's say. Then we tested in the underside direction, so we tried to bend in the opposite direction tip. And in this case, we saw that version with incision, so B and D, showed a better elastic return. After this, we decided to go for the version D, that was the one with with the incision and the abutments, because it allows a perfect 90-degree bending. At the end, after 1,000 of cycles, the bending force is slightly lower, but it's completely a reasonable value. So the tip can be for multiple actions inside the knee during the operation. The extrusion features of the arthroscopic extruder was tested by using 3 different materials. So VitroGel, VGRGD from the Well Bioscience, methylated gel and gum, so GGMA, and a blend made by alginate and gelatin. We had a rheological characterization of these 3 materials, and we saw that are perfect for this kind of studies, for this kind of investigation, because these materials are inside a power law. So these materials are a shear thinning kind of non-neutral materials. The characterization of the extrusion parameters was made because we tested 3 different dimensions of the tubes inside the cannula of the can, and because we need to know the extrusion force required for all the materials, and we needed to assess the presence of occlusion phenomena when the tip was bended. So we tried 3 different diameters, so 0.5, 1.4, and 2 millimeters. In this case, we saw that for 0.5 millimeters was very, very small, and it required a very, very high extrusion force. It was not possible to extrude with a machine or with a hand. And at the end, we selected for 1.4 millimeters, and we see that the light and darkest color are in bending the straight configuration of the tip, and we see that there are no difference on the extrusion force required by the device to extrude the material. So this is, at the end, this is the arthroscopic extruder that we developed in these months, and is composed by a handle, a trigger to bend the tip, the cannula made by nitinol, and a polymeric tube inside the cannula, and the wheel, as you can see in the video, to rotate around the axis of the nitinol tip. We protected this design by a patent, an international PCT patent, and then we started to test also the other features of the extruder. As I said at the beginning, arthroscopic extruder can be supplied by a volumetric system, so that is made by a normal controller, a linear slider, and a powering that was was made by ourselves inside our lab, and a pneumatic system that is a more professional device, was developed by a partner of my other project, and was made by a controller, a very complex controller, a pneumatic pump, and a transformer. In this case, the device looks like, let's say, more professional. So we tested the device in both conditions, with both the system for controlled extrusion, for continuous extrusion, with the volumetric system of the supply unit, or also with the pneumatic system, also in this case for the controlled extrusion and the continuous extrusion. Useful things was that we were able to control also the maximum level of pressure to use to extrude the materials. That is a very important parameters when you extrude materials with cell, and then we'll see what I mean. Let's see. We explore some computational models to verify the presence of localized peak of wash stress. Wash stress is an important parameter for the cells inside the hydrogels, because we need to be sure that the cells, after the extrusion, the cells are still alive. And from literature, we know that that the materials should not overcome the 5 kilopascal of value of wash stress. So to build the computational models, we adopt the Navier-Stokes set of differential equation, and we assume that non-Newtonian fluid, like we see in the rheological characterization, from the rheometer, we were able to extract the parameters K, and then for each materials to give to the software. And then firstly, we validate the simulation by comparing the values coming from the experiments, so the extrusion characterization, with the computational models, so with the CFD models, let's see. And as we can see, the results coming from the computational models are quite matching, let's see, the results coming from the experiments. And then after this, we simulated, and we simulated the results in terms of wash stress, and in all the cases, so coming from the volumetric system or the pneumatic system, the materials never overcame the value that was set as a threshold for the cell viability. Once made the computational system, we passed it through to the lab, so that we had a biological characterization of the cell-laden hydrogels. So we wanted to see the influence of the extrusion process on human chondrocytes to cell, and we assessed the cell viability after the extrusion process and the metabolic activity. Setting different extrusion input. One was set by the ISO standards, 1.6 millimeters per second for the volumetric system, and then we chose the minimum pressure required to extrude the materials with the pneumatic system. These are the results. The results say that after 1, 3, or after 7 days, in all the case, we had the good results in terms of cell viability for all the materials, and we can see that for the VitroGel RGD, the results are strongly better with respect to the other materials in all the days, so 1, 3, and 7 days for both volumetric and pneumatic system. Also, in terms of metabolic activity, we have 3 different plots for VitroGel, GGMA, and alginate gelatin. And also in this case, after 1, 3, and 7 days, we had a good results for all the materials, but above all for the VitroGel. The last test was the usability test. Usability test was a very important milestone for the development of this device. And to do this test, we had an ex vivo test in a telemed knee, and we asked the help of 9 orthopedic surgeons from Istituto Ortopedico Rizzoli, and each surgeon tested the extruder with both supply units, so volumetric and pneumatic, and at the end, we asked them to fill a questionnaire to assess all the capabilities and to give an overall feedback of the device. Firstly, the test was made by these surgeons, and they firstly made 4 different defects inside the knee to simulate, to mock, see a real cartilage condition after a severe condition of osteoarthritis. So 4 defects were created through graft on the cadaver cartilage tissues on the medial condyle, lateral condyle, medial tibial plate, and lateral tibial plate. And so also 2 of them are in a quite easy part, quite easy to reach part of the knee, while the other 2, above all the defect number 4 and the defect number 2, are in a complex part of the knee that are very hard to reach by using a normal syringe or by using traditional devices. So in this case, we wanted to see whether the bending of the tip really helps the surgeon when releasing the hydrogel. So as you can see in these pictures, the bendable tip was able to reach all the defects that we made, and in all the cases, the tip was always in an orthogonal direction of the defects, and was able to extrude very well the material as shown in the video. After the surgical operation, the surgeons opened the knee in a very clear, to have a very clear vision of what's happened inside, and we saw that the material released in the defects was perfectly in the defects. So all the defects were reached very well by the device, and the materials was still there also after a couple of hours, let's say. So at the end we were very happy of this kind of results. As I said, the feedback of the ex vivo test was collected through a questionnaire to identify the advantage and disadvantage of the difference of the arthroscopic extruder by using volumetric and pneumatic supply unit. So the first section was related to the comfort, and we asked if the design, how much is comfortable, or do you feel pain, or how much is comfortable the mechanism to rotate with the and to bend in the same time, and the overall feedback was quite okay, from 0 to 5, and was quite okay. The second section was related to the technical questions. So how much intuitive is the control interface regarding the supply unit? How is the maneuverability of the device? Did you easily reach the number 1, 2, 3? So it was very important for us to assess if the technical innovation of the device were really effective during the operation, and also in this case, with respect to the question regarding the extruder, got, let's say, good results from 3 to up to 5, except from the volumetric extruder unit in terms of accuracy. As you can see, the last question was not so fine in terms of results for the volumetric system, because in fact, with respect to the pneumatic one, was less accurate, let's say. The last part was the overall section, and the overall section is it was very important for us to continue investigating on this kind of device, and then who knows, pursue in a future to make a real product, because that bendable tip represented a feature that guarantees an added value, and they said yes. And if the device would be available in the market, would you use it to extrude the therapeutic materials? And the overall response was yes. So at the end, we were really happy about this kind of results. As I said before, the pneumatic supply units was better with respect to the volumetric one. Also, in this case, for example, now that we are in an advanced phase of the design, we completely dedicate our effort to develop a pneumatic supply unit, and we left the volumetric system. As the last part, we are, as I said, we are now in a phase of optimization of the device. So we are trying to understand if we are able to make a smaller diameter, make a device that can be more similar to a real product. So we investigated through only, till now, only through computational models. We investigate if some materials that are currently used in the market for the intra-articular injection, for example, if they can be compatible in terms of extrusion parameters with our arthroscopic extruder. So also in this case, we collect some data from the rheometry of these materials, and then also in this case, we made some computational simulations to investigate the lumen reduction from 1.4 to 0.4, also in that case, and we saw that also in this case, we evaluate the Walsh stress got from the simulation, and never these results overcame the 5 kilopascal set as threshold, and then investigated the extrusion force. We saw that set at 10 Newton as a possible normal extrusion force, and we saw that we can arrive to 1 millimeters to involve all the materials that we considered. If we want to reduce the lumen to 0.4, we can be compatible not with all the materials, but for example with VitroGel okay, with fibrin glue okay, with Medigraph okay, but not with all the materials. So I arrived to the end. So I want to thank my team members, that is the Regenerative Technologies Lab, and thank you for your attention. So I'm completely open to the question. I will be happy to answer all the curiosities, and also if you want also technical questions, for sure.
All right. Thank you, Guarnera, for your presentation. It was very interesting, very enlightening. And now we proceed to some Q&A sessions. We do have some here, but I also want to roll it there, and we'll go back to the other questions in the slide later. Okay. Yeah. What are the main advantages of this arthroscopic device compared to traditional cartilage repair methods?
Okay. I think that the main advantage is to really control what and where you are extruding the hydrogel, let's say. So if you go with the normal syringe from the extern of the skin, okay, you don't know where the hydrogel goes. Okay, it's an environmental extruding, but you cannot be really precise. You cannot be accurate. And if you need a very accurate treatment of the cartilage with a bendable tip and in arthroscopic condition, so with the camera and so on, you can be, I think, more effective for the cartilage treatment. So this is the main advantage with respect to the state of the art, I think.
Okay, thank you. I guess it says was in, but can you? The next question is, how does the bendable tip improve hydrogel delivery in hard to reach areas of the joint?
As I show in the video of the usability test, if you have some problems in the cartilage, for example, in the condyle, in the first part of the condyle, it's very hard to go there with a normal syringe, for example, or with a normal syringe. So when you bend the tip, you can arrive there and then be completely orthogonal to the defect of the cartilage, and then you can be able to extrude better the material. So if you, I don't know how to say, if you need to be more accurate, the traditional syringe cannot allow you to be accurate. So because of this, I think that the bendable tip can improve the treatment itself.
Good, thank you. The other question is, could this device be adapted for other minimally invasive surgeries beyond cartilage repair?
Absolutely, yes. Absolutely, yes. In fact, we are still trying to be connected with the surgeons to find also other parts of the other anatomical pathologies where we can use this kind of device. Also for the internal medicine, or also for other orthopedic traumas. So the tip is very small. So also for the shoulder, for example, or for the foods. So it's we are trying to to enlarge the application field of this device.
Okay, great. I think this next question kind of aligns with the previous one. Could this system with VitroGel be used for stem cell delivery and regenerative medicine applications?
Of course. In fact, as I introduced, the arthroscopic extruder was born within the ADMAIORA project. In ADMAIORA project, the main goal was to develop hydrogel, including embedding nanoparticles and stem cells. So this device was born with an hydrogel that includes stem cells and nanocomposite for an hydrogel that can be multi-tunable and can be responsive. So absolutely, yes, this is because we thought that the future of the cartilage regeneration, but also for other tissue regeneration, will include the stem cells.
Are there any plans to integrate imaging or sensing technologies to improve hydrogel placement accuracy?
We didn't think about this because if you use for two main reasons. The first one is technological. So embed a camera or a sensing system will make the device more complicated and probably more expensive in terms of cost. And the second reason is because you don't need, probably, because if you use the device in arthroscopy, where you have the endoscope with the camera and the light, and with the right hand you use the arthroscopic extruder, a good orthopedic clinician don't needs an additional sensing system so to see where the tip is, right?
All right. You might have already answered, but what are potential applications of this device beyond cartilage repair, such as for bone or soft tissue regeneration?
Yes. For example, we was thinking to use the device, for example, for the cementification of the vertebrae. For example, can be useful, or also for deliver local, for example, after infarction. I think that where you can make a surgical operation in arthroscopy, you can use this kind of device to release the pharmacologic materials to restore the tissue.
A few more questions, I think, here. What types of cartilage defects are best suited for treatment using this device?
The device was born in the framework of the osteoarthritis pathology. So starts with with the degradation of the cartilage thickness inside the knee or inside the other parts, if you want. And then after some years, you can have like a holes. So I believe that this kind of device can be very effective when you have a localized defect and it is a sharp defect. So probably osteoarthritis could a good example, but also a trauma, for example. If you have a trauma that damage your cartilage, probably this device can be useful.
How does VitroGel contribute to the cell adhesion and proliferation in the cartilage defect environment?
Yes, as I said and as I showed in the slides, VitroGel is a very good material to embed the cells, and because there is a compromise between very good structural hydrogel that allow a good adhesion of the cells, but are not good for extrusion. They have not a good behavior in terms of delivery. While hydrogel, it's a good material to embed the cells. After 7 days, the cells were still alive, and also probably also more for 7 days. And then also VitroGel has a very good features in terms of delivery.
Great. Did you test or plan to test another chondrocyte cells line during the process?
And not so far, not so far. So we tested only human chondrocytes. Probably to extend the usability of the device, probably we will test the device also with hydrogels and bending other kind of cells.
Don't see more questions, but I think we have one more. Are there any plans to test the system in a large animal model or human clinical trials?
We are in front of the next step now. So we are trying to understand which can be the market. And after this phase, we want to face the regulatory system and the regulatory path, let's say. And in that path, for sure, we intend to use this device in a large animal model, at least in a large animal model. Of course, it depends on investments, it depends on market, so it depends on several factors. But for sure, if we are able to actually as a good TRL, so it is in a good point of development, for sure the next phase will be the phase that will tell the device, okay, you are ready.
Great, great. We're waiting for any more questions. I'm gonna wait a few more minutes. I do not see any more at this time. So Melissa, if you go back to the previous slide, I do want to, take this time to thank Dr. Guarnera as well, but I want to do some multiple applications of VitroGel, some more webinars that we have on our website, from breast cancer model to organoid cell invasion models. And our upcoming webinar, which is the cultural alcohol out organoids with zero-free VitroGel system, that is coming on April 2nd, 11 a.m., that you can register on our website. Again, thank you, Dr. Daniela Guarnera, and thank you everyone for your continued support. Please follow and connect us on the web box on our LinkedIn or our website. Learn more about hydrogel products, various 3D cell culture applications, protocol, scientific resources, publications, and future webinars. And again, this webinar will be recorded. You can watch this shortly after we end our session, and we'll send out an email to everyone that registered to watch it on demand. And again, thank you everyone for this great presentation, Dr. Guarnera as well. And everyone have a great day. Thank you.
Thank you. Thank you to you. Thank you to you. Goodbye.